So how do you actually tell a massive, powerful machine on a factory floor exactly what to do and when to do it? Well, you have to speak its language. Today, we're going to learn the absolute bedrock, the foundational grammar of all industrial automation, PLC ladder logic. This is the language that connects our ideas to a machine's actions.
Now, the absolute genius of ladder logic is that it was designed to be super intuitive, especially for the electricians and technicians who are already out there working with physical control panels. I mean, look at this. On the left, you've got a classic hardwired electrical schematic. And on the right, that's the same exact logic, just written out in ladder logic code. It looks just like the circuits they already knew, which made switching from old-school relays to PLCs a whole lot easier.
So what are we looking at here? Well, the structure is brilliantly simple. You see those two vertical lines on the sides? Those are our power rails. And each horizontal line that connects them is called a rung. Think of it as one line of code or one instruction for the PLC. On each rung, you've got inputs, like these switches, which could be sensors or buttons out in the real world. And then you have outputs, like this lamp, which are the actions, turning on a motor, opening a valve, you name it. And the key thing to remember? The logic, the power. It always flows from left to right.
Now, just like any language you've ever learned, ladder logic has its own grammar. And let me be clear, these aren't just suggestions. They are hard rules. Following them is absolutely critical if you want to create automation that's not just functional, but also safe and reliable. You break these rules and your program is just, well, it's not going to work. Okay, rule number 1. This is the most fundamental of them all. Direction. The logical flow always, and I mean always, moves from that left power rail across all the conditions on the rung over to the right rail. Just think of it like reading a book. It only makes sense in one direction.
Rule number 2 really gets into cause and effect. See, an output is the result of your logic. It's the then part of an if-then statement. Because of that, an output can't ever start a line of logic. It has to be on the right side of the rung, and it has to have at least one input condition before it that tells it what to do. And this picture shows you exactly why. I mean, look at this. We've got an input, SW2, placed after the output lamp. That's a huge no-no. It completely breaks the whole cause and effect idea. You can't have a light turn on and then check to see if a switch was pressed. The condition has to come before the action, period.
Okay, so here's how you do it right. The inputs, SW1 and SW2, they're on the left. There are conditions. You can read this as if switch 1 is on and switch 2 is on. And the output, our lamp, is over on the right. That's the action. Then turn on the lamp. See? If, then. It's simple, it's logical, and it actually works.
So what if you have a situation where one set of conditions needs to make multiple things happen? Let's say pressing one button needs to turn on a light and start a fan at the same time. This next rule tells us exactly how to handle that. A super common mistake is to wire your outputs in what's called series. One right after the other on the same line. This is just a bad idea. It's logically flawed and it can be unsafe. In the real world, if lamp 1 burned out, the circuit would be broken and lamp 2 would never get power, right? The PLC logic works the same way. It creates this weird dependency that's just a recipe for unpredictable problems.
The right way to do it is to use parallel branches. You see how the logic from the inputs splits off here. It creates two totally independent paths to the outputs. One branch controls the first lamp, and a separate parallel branch controls the second one. So now both lamps are controlled by the same condition, but they work independently. One can fail, and the other one keeps on working. That is robust, reliable design.
All right, this rule right here might just be the most critical one for preventing total chaos in your program. Every physical output, a specific motor, a specific valve, it has its own unique address, and you are only allowed to command that address in one place in your entire program. Why? Think about it. You can't tell a motor to be on and off at the exact same time. It creates a contradiction that the PLC just can't solve.
So here's the key difference. You can check the status of a button or a sensor, an input, in 100 different places in your code if you need to. That's just reading information. But that final command, the one that actually tells the conveyor motor to turn on, that can only exist on one single rung. That's the one and only place you get to write to that output.
Okay, that's enough theory. Let's see how these rules actually play out in a real-world scenario, something you'd find on pretty much any factory floor. Let's talk about controlling a simple conveyor belt.
So here's our job. We've got a conveyor motor. We need it to kick on when an operator hits the green start button, and we need it to keep running until somebody hits the red stop button. This is a classic start-stop circuit, and it's one of the fundamental building blocks in all of automation.
Now, let's just map our scenario onto that correct diagram we saw earlier. For the start part of our logic, the start button is our input. That's the condition. And the motor is our output. That's the action. So, following the rules, the start button input has to be on the left of the rung, which then gives the command to energize the motor output on the right.
And this, right here, is why it all matters. If you follow rule number 2, input before output, the button press causes the motor to start. The system works. The production line runs. But if you break the rule, the logic makes no sense. The program will either error out or just fail, and that conveyor belt isn't going anywhere. This grammar has a direct impact on the physical world.
So, we've covered the core grammar of ladder logic. Let's boil all this down into a super simple checklist that you can just run through in your head anytime you're writing or trying to fix a program.
First, ask yourself, is my logic flowing left to right? Second, are all my inputs, my conditions, happening before my outputs? Third, if I'm controlling a bunch of things from one condition, are those outputs in parallel, not series? And finally, the big one, have I used each output address only one single time in this entire program? If you can say yes to all 4 of those, you are well on your way to writing clean, effective code.
So now you've got the basic grammar down. The next step is adding more vocabulary. Things like timers and counters. But just think about it for a second. How would you use these rules, maybe combined with some timers, to control a traffic light? You'd need 3 unique outputs, red, yellow, and green, probably on parallel branches. And you'd need logic to make sure only one is on at a time in just the right sequence. And that, well, that's where the real power of automation begins.